Hello and welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be learning about titrations. Our aim for today is how can we calculate the concentration of an unknown acid or base. An acid-base titration is a method for determining the concentration of a solution by reacting a known volume of that solution with a solution of known concentration. So, for example, if we had an acid but we did not know the concentration of that acid, we could take a base, which we did know the concentration, we could neutralize the acid, and depending on how much base we used, we could calculate the concentration of the acid. I know it sounds confusing. We'll do a couple examples together. So here we have a neutralization reaction. We have sodium hydroxide, a base, plus hydrochloric acid, an acid. Remember, when we react an acid with a base, we get a salt as a product, in this case sodium chloride, and a water molecule. Here it's telling us that since it's a 1-to-1 ratio, 1 mole of sodium hydroxide would neutralize 1 mole of hydrochloric acid. However, in the second example, we have magnesium hydroxide, MgOH2, plus 2 HCl, and here that will give us the salt, magnesium chloride, and again, a water molecule, 2 water molecules actually. So here, since HCl has 1 H, whereas magnesium hydroxide, MgOH2, has 2 OHs, it's actually going to take double the amount of hydrochloric acid to neutralize magnesium hydroxide. So, for 1 mole of magnesium hydroxide, that would neutralize 2 moles of hydrochloric acid. Let's look at the procedure for a titration next. Here we have a rough sketch of a titration. Here we have a burette. Inside the burette is a base. And here we have a flask. Inside the flask is the acid with an unknown concentration. We also put a couple drops of phenolphthalein in the flask, the acid-base indicator. Why do we do that? Well, the flask will turn pink when the acid has been neutralized. So inside the burette, once again, we have base. Here we have the stopcock, the valve. We open up the valve to drip the base into the acid, and we stop when we reach the end point of a faint pink color. If we go too far, we get this dark pink color, and our results cannot be used. We have to start the experiment over again and be a little bit more careful the next time. This is the color we want, faint pink. This dark pink would be too far. Let's look at the procedure for an acid-base titration. When performing a titration, you would want to start with a measured volume of an acidic or basic solution of unknown concentration and place that in an Erlenmeyer flask with an acid-base indicator. Today, we are going to have an unknown concentration of acid. We will put that in the flask, and the acid-base indicator we will use is phenolphthalein. Then we will fill the burette with a titrating solution of known concentration, and that is known as the titrant. So we are going to, for our purposes today, we will know the concentration of the base, so we will put the base in the burette. The acid will be in the flask, and the base will be in the burette. Then we will have measured volumes of the standard solution, and they will be added slowly to the flask. So we'll drip it slowly from the burette into the flask and swirl the solution until the reaction reaches the equivalence point. That will be that faint pink color that we were talking about before. And the equivalence point is the point in which the solution is neutral, which means the number of moles of the H plus ions, which makes the solution acidic, will equal the number of moles of OH minus hydroxide ions, the ions that make the solution basic, from the base. So once again, the equivalence point That's the faint pink color. And we reach that when the H plus ions, the concentration of H plus ions, is equal to the concentration of OH minus ions. When H plus is equal to OH minus, that means the solution is neutral. It is neither acidic nor is it basic. Let's do a titration together. Here we have a setup for an acid-base titration. We have a burette attached to a ring stand and a burette clamp. We have hydrochloric acid of unknown concentration. We have a base, sodium hydroxide, of a known concentration, 0.50 molar. We have phenolphthalein, an acid-base indicator. We have an Erlenmeyer flask, a graduated cylinder, and a funnel. Before we get started, let's take a look at the burette. The burette has graduations that go backwards. We start here at 0, and we end down here at 50 milliliters. We'll talk about why that is in a few seconds. Here we have a specific type of valve. This valve is called a stopcock. This stopcock, just like any other valve, when it is perpendicular, when it makes a right angle with the burette, it is closed. In order to open the stopcock, you turn it either way, clockwise or counterclockwise, so that it is parallel with the burette. So if the stopcock is closed, that means it is perpendicular to the burette, and if it is parallel to the burette, that means the stopcock is open. Right now we're going to close it, put it parallel. Take the funnel, put it in the top, and we're going to pour base in it so that it goes just above the 0 milliliter mark. Might be hard to see, but I went above the 0, so the 0 is right here, and the top of my meniscus is right about here. Now I'm just going to raise the burette a little bit so that I can put the beaker under it. Now I'm going to open the stopcock so that I can slowly drain the base down so the meniscus is touching the 0 milliliter mark. The reason I do this is there might be some air bubbles in the stopcock, and by filling it up higher than 0 and then slowly draining it down to 0, we can ensure that we have the proper volume of base inside of the burette. So I'm at 0. I'm going to move the base to the side, and now I have the hydrochloric acid of unknown concentration. I'm going to take 15 milliliters of hydrochloric acid. I'm going to measure it using the graduated cylinder. Make sure it is eye level and that the meniscus is touching the 15. And I'm going to pour the 15 milliliters of hydrochloric acid in the Erlenmeyer flask. I'm also going to take 2 drops of the phenolphthalein and place it into the acid inside the flask. I have this white piece of paper so that I can see the color change of the phenolphthalein when it turns pink. When the phenolphthalein turns pink inside of the flask and it stays a faint pink for a couple seconds, I know that the acid has been neutralized. So let's start. I'm going to open slowly the stopcock and drip the base slowly into the acid while stirring. So far it is clear. There has been no change yet. I can go a little quicker because I don't see any pink. As soon as I see pink, I'm going to slow this down so that I could do 1 drop at a time. to swirl as the base is being dropped into the acid. And I'm looking for any faint pink color. Make sure you're swirling it the whole time. All right, so I see a little bit of pink in there. I don't know if you could see it on the camera. So I swirl it, but when I swirl it, it goes away. So I'm going to very slowly put base in there and swirl. I need the pink to stay faint pink for about 10 to 15 seconds. That's when I know I'm done. Getting closer, but still not there yet. I know I'm not there yet because every time I swirl it, the pink goes away immediately. Getting closer. But not quite there. You don't want to go too quick because if you go too far, it's going to turn very pink and you will have to start the experiment over again. So right there we have a faint pink. We'll get a little closer. We can see it's faint pink against the white piece of paper. And our final reading on the burette is about 17.7 milliliters. Final reading on the burette, 17.7 milliliters. Now, if we were to go too far, it would be very pink. So right now we have faint pink. I'm just going to put some more in there to show you what you don't want. So right here, that is very pink. We have gone too far. What you want is that faint pink that we saw a moment ago. Here's the formula for calculating molarity from the titration data. The formula is Ma times Va, whereas Ma is the molarity of the acid, Va is the volume of the acid, equals Mb times Vb. Mb is the molarity of the base, and Vb is the volume of the base. So altogether, Ma times Va equals Mb times Vb. So we have the formula. Let's write the formula again. Ma Va equals Mb times Vb. And then we write our known and unknown values. Ma, we did not know. So we'll leave that as a question mark. Our Va, our volume of our acid, we did know, and that was 15.0 milliliters. Our molarity of our base was 0.50 molar. And the volume of the base that we used from the burette was 17.7 milliliters. So we plug those numbers in. Ma, we still don't know, times Va, 15.0 milliliters, equals Mb, 0.50 m, times Vb, 17.7 milliliters. First thing that we are going to do is multiply 0.5 times 17.7. So 0.5 times 17.7, we get 8.85. We keep the units, 8.85 molar times milliliters equals MA times 15.0 milliliters. We divide both sides by the 15 milliliters. We want to get MA by itself. So when we divide both sides by 15.0 milliliters, 15.0 milliliters, the 15.0 milliliters cancels out. So we're left with MA equals 8.85 molar times milliliters divided by 15.0 milliliters. The units milliliters and milliliters cancel out, so we're left with molar. 8.85 divided by 15.0 gives us 0.59 molar. So the concentration of our acid was 0.59 molar. Let's try another practice problem together. If it takes 25 milliliters of 0.05 molar HCl to neutralize 345 milliliters of NaOH solution, what is the concentration of the NaOH solution? And here we have 1 HCl plus 1 NaOH goes to 1 NaCl plus 1 H2O. So it's a 1-to-1 ratio. First thing we do is let's write our formula. Ma times Va equals Mb times Vb. Then we write our known and unknown values. Ma, we have HCl, so the molarity of the acid is 0.05 molar. The volume of the acid is 25 milliliters. To neutralize 345 milliliters of NaOH, so we have our Vb, which is 345 milliliters, and we are trying to find the concentration of the NaOH. So that's our question mark. We plug in our numbers, 0.05 m times 25 milliliters equals Mb, we still don't know, times 345 milliliters. Next, we multiply 0.05 times 25. 0.05 times 25 is 1.25 molar times milliliters equals Mb times 345 milliliters. We want to get Mb by itself, so we divide both sides by 345 milliliters. This cancels out, so we're left with Mb equals, and then the milliliters cancel out, so we're left with the unit of molar. So Mb is equal to 1.25 divided by 345. So we get this very long number, 0.003623188 with the unit of molar. For significant figures, we look at the least number of significant figures. 0.05 has 1, 25 milliliters has 2, 345 has 3. So we go with the least number of significant figures, which is 1. 6 is 5 and above, so this 3 rounds to a 4. So our final answer, our Mb, is equal to 0.004 molar. Practice problem number 2 states, what is the molarity of a 30.0 milliliter hydrochloric acid solution which is just neutralized by 48.0 milliliters of 0.100 molar sodium hydroxide solution? First thing we do is we write our formula. I'm going to write it here, Ma Va equals Mb Vb. Once again, same formula, HCl plus NaOH goes to NaCl plus H2O, so it's a 1-to-1 ratio. We don't have to do anything extra. So we write our known and unknown values, Ma, Va, Mb, Vb. Our Ma is unknown, Our volume of our acid, hydrochloric acid, is 30.0 milliliters. Our molarity of our base, sodium hydroxide, is 0.100 molar. And our volume of our base is 48.0 milliliters. We plug in our numbers, MA, we still don't know, times VA, 30.0 milliliters, equals MB, 0.100 molar, times 48.0 milliliters. First thing we do is we multiply 0.1 times 48.0 milliliters, so we get 4.8 molar times milliliters equals the other side, MA times 30.0 milliliters. We want to get MA by itself. So we're going to have to divide 30.0 milliliters by both sides. This cancels out, the 30 milliliters and 30 milliliters cancel out. So we're left with MA is equal to 4.8 molar times milliliters over 30.0 milliliters. The milliliters and milliliters cancel out. We're left with the unit of molarity, molar. So we do 4.8 divided by 30.0, and we get 0.16 molar. We look at our significant figures, 3 significant figures, 3 significant figures, 3 significant figures. So a better answer actually would be 0.160 molar to give it 3 significant figures, and that is our final answer. So we box it off. This last problem, problem number 4, is a little bit trickier than the other problems we've done so far. Problem number 4 states 55 milliliters of 0.30 molar KOH, so that's our base, are required to titrate 65 milliliters of H2SO4, sulfuric acid, which is our acid. What is the molarity, the concentration of the H2SO4? Now, when we write the equation, MAVA equals MBVB, there's an added wrinkle to this equation. Notice, one H2SO4 is neutralized by 2 KOHs. It is a 1-to-2 ratio. H2SO4, there's 2 H's here, H plus, whereas KOH, it's only 1 OH minus. So the H2SO4 is doubly as strong an acid than KOH's, potassium hydroxide, is as a base. So since we could say that the potassium hydroxide is half as strong as the H2SO4, there's a 2 coefficient here, we divide the base side by the number 2. It's a 1-to-2 ratio, so we have to divide the base side by 2. Everything else is just the same. We write our known and unknown values. MA is equal to unknown, we do not know that. VA is equal to 65 milliliters. MB is equal to 0.30 molar. And VB is equal to 55 milliliters. We plug it in. Do not forget about that dividing by 2. So we plug it in. We don't know MA. Times VA is 65 milliliters equals MB, 0.30 molar, times 55 milliliters divided by 2. Now when I rewrite this, I'm going to take care of this right away. So I'll rewrite it as MA times 65 milliliters is equal to 0.30 times 55 divided by 2. I get 8.25 molar times milliliters. And it's just like any of the other equations that we've done. We want to get MA by itself, so we divide both sides by 65 milliliters. The 65 milliliters cancels out, so I'm left with MA is equal to 8.25 molar times milliliters over 65 milliliters, which means the milliliters and milliliters cancel out. So I'm left with 8.25 divided by 65, and I get this long decimal, 0.126923077 molar. I look at the significant figures. 65 has 2, 0.30 has 2, and 55 has 2. 1, 2, 6, 5 and above. So my answer, my molarity of my acid is 0.13 molar. Thank you for joining Mr. Alvarez's virtual chemistry classroom. Today we learned about titrations. We figured out how to find the concentration of an unknown acid or base solution by performing a titration procedure. We learned the formula Ma, molarity of the acid, times Va, volume of the acid, is equal to Mb, the molarity of the base, times Vb, the volume of the base. Once again, Ma times Va equals Mb times Vb. We also performed a titration of our own. Thank you again for joining us. I hope you learned something today. Please join us again soon.